Welcome everyone to the sixth video here on chapter 13. In this final video, we're going to be talking about colligative properties of solutions. Okay. So colligative properties are related to electrolytes. And what is an electrolyte? Well, an electrolyte is something that dissolves in, say, water and allows that solution to conduct electricity. Water itself, pure water, does not conduct electricity. However, when you dissolve an electrolyte, something like sodium chloride, it will conduct electricity. Basically, something is an electrolyte if it dissolves in solution and creates ions, right? Sodium chloride breaks in solution and creates sodium ions and chloride ions, and those sodium and chloride ions that are free to move about in solution are what allows that solution to conduct that electricity through the solution. Okay? Without these ions, the solution would not conduct electricity. Okay? And so sodium chloride salt, right, is an electrolyte. Basically, any ionic compound will be an electrolyte in solution. Okay. Right. And so what we can ask ourselves is what happens to the properties of the solvent, of the solution, when you add some solute. Okay? And this is related to things like why we add salt to roads when it snows. Okay? And these type of properties are called colligative properties. Okay? A colligative property is a property of the solution that depends on the number, not the identity, just the amount, the number of solute particles, okay? And this property will change relative to the pure solvent, okay? So a colligative property is some property of the solvent that changes, okay? Right? When you dissolve some amount of solute in that solution, and it doesn't depend on what type of solute, just how much solute is dissolved. Okay. And some examples of colligative properties that we'll talk about are boiling point elevation, freezing point depression, vapor pressure lowering, okay, and osmotic pressure. We won't go too much into detail about osmotic pressure, okay, but boiling point elevation, freezing point depression, vapor point lowering, or vapor pressure lowering, and osmotic pressure are all different colligative properties. These are all properties of a solution that change with the amount of solute added. Okay. So in boiling point elevation, right, that is related with an increase in the boiling point with an increase in solute concentration. Okay. Freezing point depression, right, is when you increase the solute concentration, you reduce the freezing point of that solvent. Okay. And then vapor pressure lowering, right, is you increase the concentration of the solute and you lower the vapor pressure of the solvent. Okay? And so the names of these things, boiling point elevation, freezing point depression, vapor pressure lowering, right, the names are given, these elevation and depression and lowering to indicate how these properties change with an increase in concentration of solute. Okay? So boiling point elevation, how do we calculate how much the boiling point actually changes? Okay? Well, that is given by this equation here, where I is this Hoff factor that we'll talk more about in a minute. Okay, delta T is the change in the boiling point, the increase in which your boiling point changes by. Okay, and then KB is called the boiling point elevation constant. For water, for example, it's 0.52 degrees centimeters per molality. Okay. And then M here is the solution molality. So these colligative properties are often measured and determined using molalities. Okay? And so this equation determines, right, how much the boiling point of a solvent changes with the addition of some amount of solute. Okay? And these KBs, right, these constants are predetermined values through some type of experiment or things like that, right, and depend on the solvent only. It does not depend on what the solute is, it just depends on what the solvent is. Okay? So what is this Hoff factor? Well, the Hoff factor is technically defined as the measured value of a colligative property change over the expected value for a non-electrolyte system. Okay? So very complicated way of describing this, right? And again, this is the technical definition, but not practical in terms of what we kind of use in this class, okay? In general, the theoretical values that we will talk about and use in problems in this class are typically lower than the actual values, okay? So in this course, the Van Hoff factors we'll be dealing with are going to be whole numbers, 1, 2, 3, 4, 5, so on and so forth. In actuality, the numbers might be 1.4 or 2.8 or 3.7 or something like that, right? But we won't really deal with that or focus on that in this class. Okay, so right, so basically how we, in the purpose of this course, will think about Van Hoff factors is we want to think about when you dissolve something in solution, how many particles does one of those solutes form in solution? Okay, so for example, C6H12O6 will have a Van Hoff factor equal to 1 because when this gets dissolved in solution, it does not break apart at all in solution. And so one of these solute particles just forms one solute particle in solution. Okay. Well, sodium chloride is a salt, an electrolyte. This will break apart in solution. And so when they dissolve one sodium chloride molecule in solution, it will break apart into a sodium ion and a chloride ion. So my Van Hoff factor is 2. Okay. Potassium sulfate here, right, will have a Van Hoff factor of 3 because that will form 2 potassium ions and 1 sulfate ion in solution, so that Van Hoff factor is 3. Right, and so freezing point depression, right, for freezing point depression it has a very similar type of equation as the boiling point elevation, okay, that change in temperature, right, the change in your freezing point is related with the Van Hoff factor, with the freezing point depression constant, okay, and the molality, right. So the only difference between the freezing point depression and boiling point elevation equation is just the constant that's used, whether you're using the boiling point elevation constant and the freezing point depression constant, which again is unique for a given solvent. Okay, so the values given here are for water in particular, but if we used a different solvent like ethanol, they would have different values for Kb and Kf. Okay. Right, if we wanted to try to analyze what solutions might have higher or lower freezing points or boiling points and things like that, right? If all solutions have the same molality, right, the same concentration, then it just depends on the Van Hoff factor, right? That the largest change will come with the largest Van Hoff factor, right? But if the different solutions have a different concentration, then what will determine which has the greatest change in boiling point or change in freezing point will depend on the Van Hoff factor times the molality, right? So IM here is supposed to indicate the Van Hoff factor I times the molality M, right? It's not some weird word in, right? It's the Van Hoff factor times the molality, okay? And that product will determine what solution, when we're comparing different solutions, will have a greater change, right, in boiling point elevation or the freezing point depression, okay? And so that does it for our discussion of solutions in chapter 13, okay?